For reversible reaction also, I will send you a PDF, okay, about all the nodes which I have solved. It might ask the integrated rate law for a reversible reaction, okay, which will be in the fourth page of the PDF. That it will be equal to this last equation, which we took and draw a plot also. The plot is there in the PDF, you just see through it, okay, and the derivation also. So all this is the derivation of the integrated rate law. But then this will be asked for 6 marks, so for tomorrow I don't think it will come, but still in the final exam it might come, so just see through it. But the most important thing in a reversible reaction is the graph, okay, the concentration versus time graph. Just remember this. And then for equilibrium reaction, this ratio is the most important one. Like A gives B in a reversible way, okay, then we say that the ratio of A to B at equilibrium concentration will be equal to K of -1 by K of 1. This, you just remember this equation, this formula. This will be equal to the equilibrium constant K. That's all for equilibrium reactions. And then next we have the consecutive reaction, okay, this is the most important one. So in consecutive reaction, I'll send you a PDF also for this one. And the first part, I'll just write it like this: consecutive is considered consecutive reaction, and then we do the integrated rate law part, during which this reaction, after this I write Laplace transformation, okay. This Laplace transformation is a very complicated process, and Sir Chandra also didn't teach it properly. He sent us a PDF in which he was showing this Laplace transformation, but then I thought like it's better to just shorten it, because in exam we don't have to show that long, na? So even if it's asked about integrated rate law, but I don't think it will be asked, but then just write like this, okay, by Laplace transformation, like this, just by heart this equation, okay. So at case 1 we got like this, at case 2 we got like this. So this case 2 is the condition where we got a steady state approximation. And in steady state approximation, just remember that K2 must be always greater than K1. And then for case 1 we draw this graph, and for K2 we draw this graph. See this this one is touching this line, na? It should not touch, okay, it can go near here, but doesn't necessarily have to touch. Like this one, it can go near here also, same, it can go near, but it should not touch. So I'll just send you a PDF of this consecutive reaction also. Now the most important part in the consecutive reaction, see the question which the problem, the that solving problem which you asked about, that doubt which you had, it came from a consecutive reaction which is reversible in nature, okay. See, if a reaction is of this type, this is the most important reaction in a consecutive reaction, I mean this form, okay. So if the reaction is of this form, like this, and the condition is that, so as I was saying, this reaction is very important, the main this form. So in this case, two conditions are possible, okay. Either this K2 and K minus 1 is much greater than this K1. That means the rate at which B is decaying to form C or A, I mean the intermediate B is decaying from being B, okay. If that rate is much higher than the rate at which it is forming, That is K1. K1 is the rate constant for the reaction of formation of B from A. So the rate at which B is decaying, either in this direction or in this direction, is much greater than the rate at which it is forming. Then we can use steady state approximation. Okay, and we can use this equation, find out the concentration of B, and then we can use this equation to find the concentration of A. But if the rate at which B is forming product is small as compared to the rate at which this B intermediate is reversing back to the reactant A, then that means if K2 is small as compared to K negative 1, K minus 1, then in that case there exists a quasi-equilibrium, or an equilibrium process is happening between A and B. In that case, we cannot use steady state approximation. We have to use this equilibrium constant, and then we have to use the equilibrium formula. That is this one. I said now that an equilibrium exists between A and B. If this K minus 1 is much greater than the K2, then in this case a quasi-equilibrium exists between these two, right? So in this case we'll use the equilibrium constant formula. That is B by A by B will give -1 by A. Just remember that there is reverse. Okay, if you divide A by B, then it will be K negative 1 divided by K1. Then we can get the concentration of B. Okay, just remember these two conditions. So we'll see through the application of this one. Okay, so this is the question which you had doubt, no? In this case it's showing this here. See, this is a chain reaction. Okay, in a chain reaction, to the intermediates we always apply the steady state approximation always, no? Where we equate the time derivative of the intermediate equal to 0, right? That is the steady state approximation. This one, if there is a chain reaction, okay, like say A to B, then this B forms C, C forms D, and then D forms E. So this is the product and this is the reactant. Then the intermediates will be B, C, D, no? So we can apply steady state approximation like this. Say let's apply for B. The time derivative of this intermediate, we equate it to 0. This is called steady state approximation. But in this question, even though this is a chain reaction, there is a condition here. It's given that this one has a very fast equilibrium. So if it's written like this, then it means that the rate at which the reaction is reversed, that is like K negative 2 or K negative 1, this is much greater than K3, at which the rate at which products are formed. Like I have discussed before, I said now that if we consider this reaction K1, K minus 1, B, it gives C where K2. If this K minus 1, that is the rate at which it is reversed back to the reactant, is much greater than the rate at which product is formed. So I mean this one. Okay, in this case there is a quasi-equilibrium in this case, and we cannot use steady state approximation, and we have to use equilibrium constant formula. So that is why for solving this equation I used to find this. It said that show that the mechanism is consistent with the observed rate equation, which is this. So it's given that the rate equation of this reaction is this one. So it's said to show this equation is true. So in order to prove this question, in order to solve this question and prove what is said there, I have to use equilibrium constant formula, not steady state approximation. That is why I use this one. Okay, see, in this reaction I can apply equilibrium. This reaction I can apply equilibrium, but in this one I cannot apply equilibrium, okay, because there is no reverse reaction here. There is no k minus 3, only k3 is here. Here I have k2, k minus 2, k1, k minus 1 is here. Here there is no reverse reaction, so I cannot use equilibrium reaction here. Equilibrium constant formula here, okay, but I can use in the first and second reaction. And another thing is that this m is mentioned here. Actually, this m doesn't have any importance. This is added just to make us confused. This is just representing metal center. It doesn't have any importance. It's just added to make us confused. So no need to worry about it in the exam. If there is no m also, it's just the same reaction, okay. Like it maybe says C2, forget this m. Reaction in forward k1, reaction in inverse k minus 1, and then there is 2C2, no m here. Then in that case also it's just the same reaction, okay. So I said for the first reaction we use this here, and then we apply the equilibrium constant, because I said there is no steady state approximation, so we cannot apply steady state approximation, so we have to use equilibrium constant formula. So I used equilibrium constant formula, k1 by k minus 1, and here instead of writing a by b or b by a, it's just the same, okay. B by a or a by b, since there are two products and two reactant here, I just use this, okay. And while writing equilibrium constant, you should know that there is multiplication here, it's not addition here, okay. It's a formula, you have to remember that. And then I solve it, and then I solve the second reaction's equilibrium process. I solved it, and then the red equation of the overall reaction, I solve it. The red reaction of an overall reaction, that means the process at which a product is formed. Just remember that it will be given in the question, okay. In this case we are given to find this one, so just write this one. For this we know that this one is forming this reaction, so write K3 into ClCO into Cl2, like this one which I had written here. Now there comes the part where you didn't understand. K3 ClCO, I took this ClCO from this equation and right here, see this equation I got. If I keep this ClCO this side, I transfer this Cl this side, K2 this side, K negative 2 this side, and keep only ClCO, then I got the formula for ClCO now. Then I apply it here, and then for this Cl2 I use it from, where is that, this one. I keep only the Cl2 here, I transfer this K negative 1 this side, K1 this side, and then I got Cl2 value. I applied it here, and then the process is done. Like see in this one, if I keep only the ClCO, then it will be like this. I'll transfer this Cl this side, okay. CO, Cl, I transfer this K2 this side, so it will be K2, and then K negative 1 this side, K negative 2 is equal to, only ClCO is left now here. So I got the formula, I got the value of ClCO, so I just put it here instead of the ClCO. Same goes with this one. I want Cl2, so Cl2 I leave it here. This one I transfer it this side, this one I transfer it this side. I got the value of Cl2, I put it here, okay. After that I just did some calculations. This and this are just the same, so I'll just combine it. It will become Cl cube, okay. Cl2 and then Cl combined, it will be Cl cube. CO will be left, and then K2, K minus 1, K negative 2, K1, all will combine like this, and I represent this as K observation. This, so I got the formula which the question wanted me to solve, and the question is done. Now this is another question, okay, and it was asked in the previous session also. In this case, it is not mentioned that there is fast equilibrium or there is slow equilibrium, so we have to use steady state approximation here. A chain reaction is given, it is not mentioned there is equilibrium or not, so in this case we have to use the steady state approximation. Okay, I've solved this one and I have already sent. I have not sent yet. I'll send you in a while.